We left off doing some Hess's Law problems from the Part 1 lecture. So I'm going to start off this lecture doing one more practice problem using Hess's Law. Why don't you pause the video and see if you can figure it out. Here is this problem worked out. And sometimes hearing it in a different voice or in a different way can help it click. So listen to their solution.
Problem. We are going to show the value of Hess's law for the determination of enthalpy changes in chemical reactions. Suppose that we want to know the enthalpy change for the formation of methane from solid carbon and hydrogen gas, as shown in the balanced equation. To determine the enthalpy change in the laboratory, this reaction would have to proceed at both a reasonable speed and it would have to proceed to completion. Unfortunately, it doesn't. Luckily, there are ways to get around this problem. Both the reactants and product undergo reactions that can be studied in the laboratory. For example, carbon can be combusted to form carbon dioxide. Hydrogen will react with oxygen to form water. And finally, methane reacts with oxygen to form carbon dioxide and water. We can use the data from these three reactions to determine the enthalpy changes for the formation of methane from carbon and hydrogen. So what do we know? Foremost, we know that this is a Hess's law problem. We can adjust the three thermochemical equations so that they add together to give the desired equation. If the equations are properly adjusted, the enthalpy changes for the reactions will add together to give the enthalpy change for the desired reaction. This problem cannot be solved by simply adding the equations together in their current form. We need to manipulate both the equations and the enthalpy changes first. A couple of things to think about. If we reverse the direction of a reaction, the sign on delta H changes. If we change the amount of reactants and products, the delta H value will change proportionally. Okay, so let's start by determining what, if anything, needs to be done to the first equation. Notice that both equation 1 and the overall equation contain carbon. Additionally, 1 mole of carbon appears as a reactant in both equations. No changes are needed for equation 1. We are not as fortunate with the second equation. We see that both this equation and the overall equation contain hydrogen gas as a reactant. However, equation 2 is written for 1 mole of hydrogen gas, where the overall equation requires 2. This is easily fixed by doubling the stoichiometric coefficients in equation 2. It's important that we remember to also double the enthalpy change from negative 285.8 kilojoules per mole reaction to negative 571.6 kilojoules per mole reaction. I'm going to go ahead and use a prime signal to designate the adjusted reaction. We see that equation 3 and the overall equation both contain methane gas, but on opposite sides of the equation. Reversing equation 3 results in methane as a product. It also results in the opposite enthalpy change. So the enthalpy change for the adjusted reaction, which we will designate as equation 3 prime, is positive 890.3 kilojoules per mole reaction. All that remains is to add the three reactions and their enthalpy changes together. It's easy to verify your work. Cross out the species that exist equally on both sides of the equations. Make sure that you are left with the correct reactants and products in the correct stoichiometric amounts. When the three enthalpy values are added together, the sum is negative 74.8 kilojoules per mole reaction. We now know the enthalpy change for the formation of 1 mole of methane gas, even though we could not actually carry out this experiment in a lab. One final note before we finish. Hess's law works because enthalpy change is a state function. No matter how you get from reactants to products, the enthalpy change is the same. The formation of methane from elements could not be done directly, but we were able to determine the enthalpy change nevertheless using reactions that can be carried out.
So calorimetry and the application of Hess's law have made available a great many delta H values for chemical reactions. We've been looking at chemical reaction. The table in the back of the book, for example, lists standard molar enthalpies of formation. Standard molar enthalpy of formation is the enthalpy change for the formation of 1 mole of a compound directly from its elements in their standard state. Let's look at a few examples of what this looks like. If I wanted to look at the enthalpy of formation, notice that it's denoted as HF for sodium chloride. I want 1 mole of NaCl. That means NaCl is made up of sodium, Na, and Cl2 actually, because it's diatomic when it's by itself. But I only want 1 mole of NaCl, so therefore I need to have half of a Cl2 plus Na. And so then I can look in the back of the book and it tells me that the heat of formation of NaCl is negative 411.12. Again, note the fraction is required because chlorine gas in its standard state is diatomic, Cl2. We could look at the heat of formation for NaCl that's in aqueous form, and so it's going to be the same equation, it's just going to be aqueous, and we would see that the heat of formation of that is negative 407 as opposed to negative 411. The heat of formation of solid sodium chloride is more exothermic than aqueous sodium chloride. I mean, not by much, but it is by, about 4 kilojoules. You can also look to see the heat of formation of ethanol at 25 degrees. We would look at what is made up of C2H5OH. Well, the elements that make it up are carbon, and in its natural standard state, carbon is a solid. Hydrogen also makes it up, and remember that's diatomic, so H2. And oxygen, and that's also diatomic, so it's O2. Now, we only want 1 mole of C2H5OH, so we need to go, okay, well, that takes 2 moles of carbon. We need 6 hydrogens, so 3 moles of diatomic hydrogens. And there's only 1 oxygen, so we only need half of a mole of O2. Now, if you flip to the back of the book or whatever appendix you're using to look at different enthalpies of formation, notice that the standard enthalpy of formation for an element, so if I just looked at oxygen in its standard state, so O2 is 0. Carbon in its standard state, which is solid in graphite form, is 0. Now, carbon as a gas is not standard state, so yes, there is enthalpy of formation for that. Carbon as a diamond is not in its standard state, so it is not 0. But elements in a standard state are 0. Most delta H values are negative, indicating that forming most compounds from the elements is exothermic. Very few values are positive, and those represent compounds that are pretty unstable with respect to decomposition to the elements. So these couple that are positive are pretty unstable. The values of these heats of formation can be used to compare thermal stabilities of related compounds and see, which is more stable. Obviously, the exothermic, the negative 273 is more stable than HI, hydroiodic acid, which is positive 25, so that's less stable. Let's do a couple examples. We did A and F. So why don't you try letter B? Write the thermochemical equation representing the standard enthalpy of formation for glucose, C6H12O6. Why don't you pause and try to do that one? And also, why don't you try to do letter C? We'll do B and C together. If I'm trying to create, we're looking at B first. I'm going to have carbon in its standard state is just solid carbon. We know hydrogen in standard state is diatomic, and that's a gas. And oxygen in its standard state is O2 as a gas. And we want 1 mole of C6H12O6. All right, so I need 6 carbons. I need 12 H's, and I need 6 O's. There we go. We would just need to look up in our appendix to see what C6H12O6 enthalpy of formation is. The second thermochemical equation we'll write, letter C, calcium carbonate. Calcium in its standard state is solid, plus carbon in its standard state is solid, plus oxygen is O2, gas, creates CaCO3. So I need 1 calcium, 1 carbon, and 3 oxygens. To get 3 oxygens from 2 oxygens, 3 halves, right? 3 times 2 is 6 divided by 2 is 3. There we go. So again, we were forming 1 mole of calcium carbonate. So moving on, we can also calculate enthalpy change for a reaction by using the standard molar enthalpies of formation and this equation. So to find the enthalpy of the whole reaction, we can take the sum of our enthalpies for our products of the formation minus the sum of the enthalpies of the formation of the reactants. Now we do have to take into consideration moles. We're going to do an example here. So the sum of, we need to take the number of moles times the heat of formation. So multiply heats of formation of products by the number of moles, add them up, and then minus sum of the formations of products as they're multiplied by the number of moles. And we'll make more sense out of that in this next problem. Here we have calcium carbonate decomposing into calcium oxide and carbon dioxide. Now you might be asking yourself, cool, I just did this using Hess's law. Where are my equations 1, 2, and 3 where I can then rearrange them, flip them, divide things by 2, multiply by 2 so that I can calculate my overall delta H? Well, in this case, we're not given those. So how can we find them? Well, we can use the enthalpies of formation from the appendix to then use this method to find our delta H. And we want to know how much energy is required to decompose 1 mole of calcium carbonate to calcium oxide and carbon dioxide. So if we look up in the back of the book and the appendix to find the heat of formation or the enthalpy of formation for each of these compounds, it tells us that calcium carbonates, calcium oxide, carbon dioxide, these are all the enthalpy of formations for these 3 compounds. So all we need to do is to sum up the products. Here's our products. So calcium oxide, there's only 1 mole of it, so I'm going to take my calcium oxide, which is negative 635.1, plus my carbon dioxide, which is negative 393.5. So here's my products, and there's only 1 mole of each of those, so I'm multiplying these by 1. Products minus reactants. My reactant is just my calcium carbonate, which is negative 1207.6. And if I plug this into my calculator, I get my heat of the reaction of plus 179 kilojoules, simply by just taking the sum of my products minus the sum of my reactants. Let's look at another example problem similar to the last one. This just adds 1 extra step. So we have nitroglycerin, which is a powerful explosive that forms 4 different gases when detonated. So here's our nitroglycerin. It forms nitrogen, oxygen, carbon dioxide, and water. We want to calculate the enthalpy change that occurs when 10 grams of nitroglycerin is detonated. Okay, so we're going to get to that in a minute. The standard enthalpy of formation nitroglycerin is negative 364. So I'm going to write that right here, negative 364 kilojoules per mole. Use the appendix to find the other values. Well, all right, we know that single lone elements in natural state, so this nitrogen, we know is 0, right? 0, heat of formation for nitrogen and for oxygen, 0. But we can look at the back of the book and see that CO2 enthalpy of formation is negative 393.5. And for H2O gas is negative 241.8. So let's find our delta H for the reaction, our delta HF. So we need to do products minus reactants. I've got my products, 6 moles of negative 393.5 plus 5 moles of negative 241.8. That's my products minus reactants. I have 2 moles of negative 364. Let's do this here. All right, so I got delta H, this whole chemical reaction of negative 2842 kilojoules per mole. Again, if I go back and look what I just did, I was given delta H, the standard enthalpy of formation for my nitroglycerin. I know that my elements are always 0. For CO2 and H2O, we were given those, or we could have looked them up in the appendix. And then I did products. I remember I had to take those numbers and times it by how many moles there are of it. So there was 6 moles of carbon dioxide, 5 moles of water, minus reactants. There was 2 moles of the nitroglycerin. So products minus reactants to get my delta H for the whole reaction. That should be RXM reaction. I want to know the enthalpy change that occurs when I have 10 grams of nitroglycerin. So hopefully you're at the point now where you go, oh, 10 grams. I need to get grams to moles. Okay, so we're told nitroglycerin is C3H5. parenthesis, NO33. This is our nitroglycerin. So grams, we need to find the molar mass of this, of 3 carbons, 5 H's, 3 N's, and 9 O's. And if we add it all up, we should get molar mass of 227.1 grams of nitroglycerin. I'm just going to write nitro G for 1 mole of that. And 10 times 1 divided by 227.1 should give us 0.04403 moles of nitro G glycerin. I'm just abbreviating for the sake of time here. To find the enthalpy change that occurs when I have 10 grams of nitroglycerin, so I'm going to start with my moles, 0.04403 moles of nitroglycerin. I know that there's 2 moles of nitroglycerin in this whole reaction, 2 moles of nitroglycerin, and I know that in this reaction there's 2 moles of nitroglycerin reacting, and that my delta H for that reaction is negative 2842 kilojoules. So I can use that delta H that I found from my products minus reactants. I went from grams to moles, and I just went, oh, for 2 moles of nitroglycerin, this much energy is released. So now I have my last part is 0.04403 times negative 2842 and divided by 2. Negative 62.6 kilojoules is my enthalpy change when I have 10 grams of nitroglycerin react. All right, let's do one more here. The question wants us to calculate the standard enthalpy of combustion for benzene. And we're given the equation here. We've got benzene plus oxygen. That's a combustion reaction to give us CO2 and H2O. And we're given that the enthalpy of formation of benzene is plus 49 kilojoules per mole. And then I looked in the appendix to find the enthalpy of formation of CO2 and H2O. So we need to do, again, products minus reactants. So we're going to do 6 times our CO2 value. So 6 times negative 393.5. I'm just going to leave off my units. They're all in kilojoules per mole, so we'll do that at the end. Plus 3 times water's value, negative 285.8. Okay, so products minus reactants. So let's do minus. There's 1 mole of benzene, so 1 times 49. And remember, lone elements that are in their natural state are 0. I mean, if you really want to put 15 halves times 0, I mean, go for it, but you don't need to, because anything times 0 is going to be 0. So 49 plus 0, we can just leave it off. So we should have a delta H for the reaction of negative 3267.4 kilojoules per mole. I'm going to put up a few more examples. If you are interested, feel free to work through them. If you feel like you've got this down pat, you can feel free to skip forward to the end of the lecture. But I'll put this up, and I encourage you to pause the video, work through it, and in a minute I will put up the next slide that has the answer on it so you can check your work. So hopefully you worked through this, given the enthalpy of formation of those compounds, and you got the answer of negative 2801 kilojoules. Let's try another. So you got negative 319.7. What's the value of this one? Unknown, delta H question mark. How would I find that? Hopefully you got negative 56.6 just by subtracting. How about this one? Which equation below defines the standard molar enthalpy of the formation of methanol? Hopefully you chose this one, because remember, if we think about ethanol, what makes it up? Carbon in solid state, hydrogen, gaseous hydrogen diatomic, oxygen, gaseous oxygen diatomic. This is not an element in its standard state. This is not element in a standard state. This is not element in a standard state. All right, what about another one here? See if you can work through this one, and hopefully you got the answer of. Let's do another one. Calculate the standard enthalpy of reaction for this process. And the answer is, see if you got the right answer, hopefully. I've got 2 more for you, 2 more. And the answer is, and finally, here's your answer. So that takes us to our very last section here, where do we have reactant or product-favored reactions? We've done a lot of thermodynamic practice in this section. The first two questions that we address, like how do we measure and calculate the energy changes associated with physical changes in chemical reactions? What is the relationship between energy changes, heat, and work? We addressed in this chapter, but the other two questions that we wanted to look at in this section, like how do we determine whether a chemical reaction is product-favored or reactant-favored at equilibrium? How can we determine whether a chemical reaction or physical process will occur spontaneously, that is, without outside intervention? Those we still have, and we're going to look more into that in Chapter 18. We can, however, set the stage for consideration of these issues. So back in previous chapters, we learned that chemical reactions proceed toward equilibrium, and spontaneous changes occur in a way that allows a system to approach equilibrium. So reactions in which reactants are largely converted to products when equilibrium is reached are said to be product-favored at equilibrium. Reactions in which only small amounts of products are present are called reactant-favored at equilibrium. In most cases, product-favored reactions have negative values of delta H for the reaction, and reactant-favored reactions have positive values of delta H for the reactions. As we can see in this example, we have a product-favored oxidation of iron. This reaction has a negative value for delta H, so it's product-favored at equilibrium. We can see that this iron powder sprayed into a Bunsen burner flame is rapidly oxidizing and it's exothermic. Conversely, we have the decomposition of calcium carbonate. It's endothermic. We can see that we have a positive value for our delta H, so it is reactant favored. That wraps up our chapter over the principles of chemical reactivity, energy, and chemical reactions. Please see our course page for additional practice problems as well as end of the chapter problems for some more practice.